Good afternoon. Thank you for the presentation. I am Terrero, and today I'm going to present this work, which is about non-smooth towing systems or a type of floating offshore wind turbine. This work was done in collaboration with the Kelvin Hydrodynamics Laboratory from the University of Strathclyde, with Saisho Dai and Jim Papadopoulos from Omega Wind and from the National Decommissioning Center and also the University of Aberdeen in collaboration with Richard Nelson and Nancy Gatlin. So first of all, I will give a brief introduction about what has motivated this work. I will talk about the aim and objectives, and then I will describe the methodology used in order to reach the main objectives. Then I will describe the system, which is a floating offshore wind turbine and also towing a piecewise linear system to tow this offshore wind turbine. Then I will present some simulations and the validations done in the offshore wind turbine, and also I will present at the end some dynamics of the system, and I will give some concluding remarks. So the necessity of energy harvesting from deep sea waters have motivated this work since offshore wind is steadier and also it can reach higher wind speeds. The current technology that we have for harvesting offshore wind energy is generally fixed to bed, so it's unfeasible over depths of over 60 meters. And the energy that can be harvested from offshore wind turbines currently is only represented the 0.29%. So there's this necessity of a new concept. The towing system that we are going to present for this for light floating offshore wind turbines will reduce the levelized cost of electricity of this type of devices, since will help us to reduce the offshore maintenance costs and will be easier to deploy and decommission. So with the marine simulator that we can see here on the right side, we're going to study this non-smooth piecewise linear system for the towing the floating offshore wind turbine that will be able to limit the undesired forces that are generated between the turbine and the attack. And we will study and we will do this study with a general attack. So the aim is to limit and reduce the forces transferred between these two components. And in order to do this, there are two main objectives. The first one is to study the dynamic interaction between the floating offshore wind turbine and the tap when connected with this non-smooth piecewise linear system during the operations. And the second is evaluation of the floating offshore wind turbine under different responses with this linear system. And so the first step was to generate a model. It was done with SolidWorks, and there are two models generated. One is the piecewise linear system, and the second one is the floating offshore wind turbine, which is the concept was brought by Omega Wind. And in this model, we adjusted the two parameters. Then we include our model into the marine simulator, which is a big simulator at the National Decommissioning Center, where we perform several simulations with different wave parameters, such as changing the wave height and wave period. And this was done for two types of sea states. So for high sea states, for wave heights between 4 and 12 meters, and low sea states. And also we vary the steepness. The model was validated with an experimental test, a prototype of 160 in a wave height. And the responses were validated for the concept of the floating wind turbine, the target we use for the model, and the connection of the floating wind turbine and the tap with this piecewise linear system. Finally, we studied the dynamics, where we identify the response varieties and also the resonance frequencies. And finally, we studied this towing system by changing the type of stiffness of one of the cases, and also by we compare it with a similar system, but in this case it would be states. So here we have the model, and the model performing SolidWorks contains the floating offshore wind turbine that we can see here. It contains it's a 6-degree of freedom system. Each component, so it's composed by 4 floaters, the structure, and the blades, and also the generator. Each component has 60 degrees of freedom, although because of the interactions between the components, we are considering that these are rigid body around the center of gravity, attack, and the visual linear system. In the model, we are just the center of gravity with the masses of each part, and then the buoyancy is provided with some air volumes included in the floats. This is the model for the visual linear system that we can see here. This is composed by 2 visual linear systems, and this one is one, and this the second. It contains each part contains an internal pipe and an outer pipe that one can slide along the other one, and it has a connector of a stiffness that we can change in the simulation. For the model, we are adjusting the stiffness of the internal pipe, and also the geometry. We are giving a geometrical boundary that is we call alpha. And also we are adjusting a stiffness of the connection between the tag and it's part of the visual linear system. So the model is imported in the simulator that it has 3 parts. So the part that in the interaction between the user and the computer, that also includes a 300 immersible environment that where we can manipulate each component. We have a scene design that is it contains the sandbox software for the visualization interface, and the engine is the Phantom software of computation that includes the algorithms AGX hydrodynamics model. So in this model, we are considering the inertia and the mass, the damping, the stiffness, and the hydrodynamic forces for each degree of freedom of each component. And the hydrodynamic forces that the system is considering are the drag and lift forces, the buoyancy forces, the current and wind forces, so the relative interaction between the object and the velocity of the field, and the inertial forces. And the main ones that we are considering are the radiation, first order, the wave dispersion, and also some second order forces such as the wave. So with the model responses, we are evaluating something called the response amplitude operators, the REOs, for the structure and the towing system, and also the tag. And so by evaluating our parameters such as height and period, we can evaluate the type of responses for subsea conditions between 1 and 2 meters of wave heights, and rough sea conditions between 4 and 12 meters. How we evaluate these REOs is the relations between the displacement of each degree of freedom respect to the wave amplitude. And here we have an example for the 2 parameters that we are considering, which is the heat and the pitch displacement. So the vertical displacement and the angular displacement respect to the y-axis. So the model was implemented, and then we do some validation of the model. Here we have a scale 1/60 prototype of the floating turbine, that was developed by T Omega and at the University of Strathclyde in the Kelvin Hydrodynamics laboratory. They performed some experiments. So here we have an example of the wave time test and the structure that is being evaluated for example of wave of 4 meters and period of 15 seconds. And the scale was done with product scaling, and the prototype was scaled 1/60. So we calibrated the model. We calibrated our model with this experimental test, and there were 2 cases. So the first case is where we have the low sea states. for the low sea states, we only calibrate with the pitch damping coefficient. And here we have an example of the results. So for the heat REOs and for the pitch REOs of a wave excitation of 2 meters, well, we see that this X blue axis represent the simulation results, and the red dots represent the experimental results. And here we have the damping adjustment for a range of one periods between 4 and 28. For the case of higher wave heights, so between 4 and 12 meters, we did the same, and here we have but in this case we adjusted 2 parameters, so the pitch and the feed. And here we have an example of the final results. So these star dots represent the low wave heights that I just showed, and this blue dashed line represent a fit that we did that, and the rest of dots represent the for higher wave heights, and the black dashed line represent for the fit for areas of the higher wave heights. Here we have the adjustment for damping parameters in the case of the heat damping and the case of the pitch damping for all cases studied. Okay, and here we have just for the visualization of how the validation was done. So we have the experimental test in the hydrodynamics laboratory, and this is our model in the simulator. So we can see that the heat and the pitch damping, the heat and the pitch statements were accurate. So finally, once we got the floating offshore wind turbine model and adjusted, we started the towing system, the piecewise towing system, and we evaluated against the heat and the pitch REOs for the tag, so for this both here, and for the turbine that we already validated for the not connected turbine. So with the connection of the piecewise linear system, we gave different parameters of the stiffness of it, and we evaluated the responses of the tag when the piecewise linear system is like a rigid body, which is this black line, and when we add some stiffness to it. And for the case of the tag, we don't see such as big differences, but for the turbine, we see that for the case of the piecewise linear system with the stiffness added, we can obtain better results for the heat REO, so this blue line. And for the case of the pitch, we can reduce the pitch REOs considerably from the turbine without the connection, although for the case of the rigid body doesn't have a much change. So with the model evaluated, finally, we can study the different types of system responses for the floating offshore wind turbine. And here we have an example of floating offshore wind turbine with wave heights of 6 meters, although we have done it for low sea states and also high sea states. So these are the REOs for the heat and for the pitch, and this color red area represent the period 1 responses. This green one represents the period 2, and this blue one period 3. From the results, we have seen that for low sea states, so between 1 and 2 meter wave heights, we only have period 1 responses, although for higher sea states, we can see more variety between 3 and between 1 and 3 period responses. We evaluated the concavity sections, phase place, and also we did an FSP analysis, and here we have an example of what we visualize in the simulator for period 1 and period 2 responses. So finally, I will give some concluding remarks about this work. We have used this marine simulator in order to predict accurately the system dynamic responses of the floating turbine and also the towing system for 2 case scenarios for low and high sea states. We have modeled our model was adjusted for 2 cases, so for the heat and for the pitch, and this was done with experimental results from the Kelvin Hydrodynamics laboratory, and we were able also to generalize our area of responses for these two cases, for low and for high systems. So finally, for our with the piecewise linear system, Turbine system, we are able to prove that we can mitigate the vibrations between transfer between our turbine and the tag. We reduce the turbine heat and pitch area responses, especially the pitch, and the system will present a better performance with this proposed piecewise linear system in comparison with the rigid body, which are the conventional ones. Finally, we were also able to investigate the resonant frequencies of our floating offshore wind turbine, and also identify ranges of parameter values where we had pitch displacement higher of 10 degrees, which can lead to a system in parking status. Although the ranges of parameter values that we obtained were only for very high sea waves. And finally, for any case, we haven't observed any case where the system is not able to return to its equilibrium point, so that we can say that we have a robust and safe system. And finally, I can say that this work was not only for regular states, although it would be good to implement the same model under different wave profiles and also different wave spectrums, as I did also. Thank you. I would like to thank you, the National Decommissioning Center and the University of Aberdeen and the Net Zero Technology Center for funding this research project, and the Omega for proposing the concept of the floating offshore wind turbine, and the University of Scotland for the experimental. Thank you.